Hey everyone, welcome back to Mr. Nelson's class, and today we're going to do 5.1 electron arrangement in atoms. Basically, we're talking about electron configurations. So we're going to talk about those and teach you how to do those in a couple of different ways. But we got to start off with a little bit of information that we have. So what makes an electron configuration of an atom stable? Well, what makes it stable is to make sure that we have that of an noble gas would be really stable. Okay, what they're going to say is that the energy and the stability play an important part in determining how the electrons are configured. And there's a certain way that they're configured, and there's rules that tell us how to configure them. And so those are what we're going to follow. So there are 3 rules for writing electron configurations of elements. Okay, and the arrangements of the orbitals and everything else that we're going to talk about, we're going to show you, and we're going to give you pictures and diagrams, but you're really going to have to learn that the first 2 columns of the periodic table represent the s orbitals, and I'll just tell you this: the first 2 columns, s orbitals. The last 6 columns represent p orbitals. These transition metals here represent the d orbitals, and the inner transition metals down here represents the f orbitals. So we're going to go back to that because that's an important concept, okay, for us to know. So here are the 3 rules: the off-ball principle, the Pauli exclusion principle, and Hund's rule. They tell us how the electrons fit within the configurations of the atoms and how we're supposed to do it. Well, we can start off with the off-ball principle. And the biggest thing about the off-ball principle is it says that the lowest energy levels get filled first, which kind of makes sense, okay? And here's our orbitals, our s. Notice we have p's, we have d's, and we have f's. But notice also that there's 1 s orbital for each energy level. So these numbers at the beginning, the coefficient numbers, they mean the energy level, okay? Now again, if I went back to the periodic table, I would say that I have 2 columns in the s orbitals, which means that each orbital can only hold 2 electrons. Okay, so I get to here and I see that I'm in p. I have 3 orbitals. Each one holds 2 for a total of 6. That's the last 6 columns of the periodic table. I go here to the D, and I have 1, 2, 3, 4, 5. And if we notice the transition metals, there are 10 across there, so each one holds 2 electrons. And the F is the same thing. There's 7 across here, so there's 14 inner transition metals. Okay, so we have the off-ball principle here, and we're going to say that it's really showing the relative energy levels, okay, as we go up through this diagram up to the top. And we're going to show you other ways to do this also. Now, sometimes these energy levels overlap a little bit, especially when we talk about the transition metals. And we just want to make sure that you kind of understand as we go through how it works. Okay. Now, the Pauli exclusion principle basically says that, according to this, an atomic orbital may describe at most 2 electrons. So it's basically saying that each orbital can only hold 2 electrons. But notice here that it says that they have opposite spins. So if I said one spin clockwise, the other one would spin counterclockwise. Or if I said one was spinning up, the other one would be spinning down. Okay, so we have a difference there. Okay, so a spin is a quantum mechanical property. Okay, and again, you can think of it as clockwise or counterclockwise, or we can think of it as up or down. Okay, so an orbital containing both electrons with a spin up and a spin down means that it's full, or you have a paired electron, so they're paired. Unpaired would mean that the box would only have 1 arrow in it. Okay, now Hund's rule basically says that if we have a box with an arrow in it and that arrow is pointing up, that if there's more than one orbital in that particular energy level, like the p orbitals, there's 3, we'd have to go up and then go to the next orbital and have one going up, and then go to the next orbital and have one going up, before we went back and filled the ones that are going down. So it's saying we're going to have the 3 boxes, one going up, 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 and then we'll go ahead and start going down, down, down. And that's what it says. So I'm going to go ahead and show you a couple ways on how to look at the electron configuration. One of them is this way right here, and the other one is in our packet. We have a couple of them in our packet. And I'm going to scroll down to our, right here. This is our configuration on how to figure out where you're at on the periodic table, okay, with the correct electron configuration. So here we have 1s2. Notice that with the arrow, we're going to start here, and we're going to go down, and we will fill 1s first, both 1 and 2. Then we're going to come back up, and we're going to go down and fill 2s2. Okay, 2s, both. Then we're going to go back here and fill 2p6. Then we're going to go to 3s2, and notice we're going right back up here, and we're down 3p6, 4s2, 3d10, 4p6, 5s2, and so on as we go all the way through it. Now I can go ahead and show you again how we do that on the periodic table. So let's pull up the periodic table, and let's just go ahead and do that real quick. Okay, so my first energy level is this one right here. Notice I have 2. So here's my 1s2. Then I go down to the next period. Okay, my next energy level is 2s1 and 2. And then I'm 2p 1, 2, 3 through 6. Then I'm going to go down to the next one, and notice that I'm 3s2, 3p6. And over here I'm at 4. So this is the fourth energy, 4s2. Now these are the D's here, but unfortunately the D's lag behind the energy level. So this is 4s2, and this is 3d all the way through here is 10, because there's 10 elements. And this is 4p 1 through 6. When we get down to this one, we have 5s2, 4d10, 5p6 are these ones right here. And this right here is 6s2. And then we have a little bit of a glitch that we have. This one right here, notice, and then we have the F's. So if I stopped here, I would have 6s2, and then it would be 5, okay, 5d1. Then I would go after this. So and then I would do these ones, and we'll talk about that in a little bit. That they're a little glitch, and we'll practice it in the real world too. Okay, so let's go back to the slides here. Okay, so notice that each one of these elements has its own electron configuration, and we can tell what element it is by its electron configuration. But one of the unique things is if we tally up all of these superscripts, okay, if I notice this, I have 1, 2, 3, and that says it's lithium. If I go back to the periodic table, well, lithium has atomic number 3, so it has 3 electrons. So it's easy to figure that out, okay? So let's go ahead. So the 1s orbital has 2 electrons with opposite spin. That's this one right here. This would be a paired electron. This would be a unpaired electron. And notice that we can see that over here. And as we go up, we're going to keep doing this. And then we fill this one. Here's carbon is 6. Now notice a 1, 2, 3, 4, 5, 6. And again, when nitrogen is right next to it with 7. And how it fills and keeps going through. Okay, so the 2s orbital has 2 electrons with the opposite spin, and so on. Okay, notice that the 2p right here, again, we're going to fill one at a time all the way across, then go back and fill the next one in as this one right here is right here. So we're going to fill all the way across one each and then go back. When we get to the D's, it'll be the same way all the way across. And then we'll come back. Now, there are some exceptions to these rules, and we'll talk about this. So the convenient way to write the electron configuration, and again, we'll just show you real quick how to write the electron configuration. We indicate the number of electrons occupying the sublevel with a superscript. Now remember, superscript, how do we get this superscript? Control greater than gives us a superscript. If we want to go back down, control greater than, excuse me, that'll bring us back down. So for hydrogen with one electron, and that is going to be in the 1s orbital, we would write it as this, 1s1. If we had oxygen, we would, and now notice oxygen has 8, so we start off with 1s2, 2s2, 2p4. If I went back to the periodic table, we would see that I would have 1s, 1 and 2, 2s, 1 and 2, 2p, 1, 2, 3, 4. Okay. Now, if I went to our electron configuration sheet that we have, and I believe it's right here, we would start up here, 1s2, 2s2, 2p. Now that's where it would end, because I would count these. I would 1, 2, 3, 4. Then I need 4 of these. So I wouldn't put down 2p6. I would put down 2p4, because that's where I'm going to end at. Okay. So let's go ahead and go back to our slides. So notice that the sum of the superscripts equals the number of electrons in the atom. Okay, so explain why the correct electron configuration for oxygen is this, not this. Well, if we look at it, we said that the p orbitals, there are 3 of them, but each one can hold 2 electrons. So I would have 2p, and I only need 4, so that would be a number there. I didn't get to the next energy level. And if I actually went back to the periodic table, I think that's represented a little bit easier there with, I'm not in the 3rd energy level. Oxygen is in the 2nd energy level, the 2nd period. So it's going to end with 2s, 1 and 2, and then 2p, 1, 2, 3, 4. This whole column is going to be p4. This whole column is going to be p1. This whole column right here is going to be s1. This whole column would be S2, and these are the Ds, D1, 2, 3, and all the way through to the end. Now remember, hydrogen is going to be over here when we talk about electron configuration. And when we get down here, these ones right here are your Fs. Remember, these are Ds, these are S, because remember, these go in right here, and then they spread apart. So here's your Fs, and it would be F1, 2, 3, 4. But again, Fs are 2 behind the Ds, and D or 1 behind the Ds, 2 behind the S's. So if this is period 6, my Ds are 5, my Fs are 4. And if we went back to our example, okay, that we have right here of the, you'll notice that if I shrink this up just a little bit, that's the way that it goes. And notice that I have 6s2, and then I have 4f14, and then 5d10. Now there is a glitch that I said that we're going to catch. That glitch is this. If I stopped here, I have to have a 5d1 in front of that. And that's because of the way the periodic table is laid out. But this will show you the exact order of the numbers. The periodic table will also do that once you know how to read that. Okay, which I think it's a lot easier to use the periodic table. So this is their answer. The 2p orbitals are lower in energy than the 3s orbital, so they will be completely filled before any electrons will be found in the 3s orbital. That's Aufbau's principle. And since p's can hold 6, this one has to go into the p before it fills the 3s. Okay, so the atomic number of phosphorus is 15. How do we write that? Okay, I'm going to show you how I would do that. Okay, I would pull it up right here, and I would go down here until I get to 15. So I start up here, and I write 1s2. There's 2. 2s2. Now we're at 4. 2p6. We're at 10. 3s2. Now we're at 12. Now we're going to add 3p, we're at 12, 13, 14, 15, so it's going to be 3p3, and that's where I would stop. Now if I went to the periodic table, I could tell you that I'd look at here, I'd be 1s2, 2s2, 2p6 through there, 3s2, and then 3p1, 2, 3. And I end up with the same one. I know that I'm going to end with a p3. Okay, so if you look at that, you can see we can count over and figure out exactly how many we have. And that's how we write out our electron configurations. So we know that, again, each orbital can only hold 2 electrons. They finish all the orbitals before they go back, and I should say they put 1 in each orbital before they go back and fill the other ones up. And so that's why we'd look at it. So we'd end up having it this right here again, 1s2, 2s2, 2p6, 3s2, and then 3p3. And that would be that. Okay. So we'd write the electrons can do that. And how can we double check this? Well, we double check it by tallying up the superscripts. 2, 4, 10, 12, 15. Excuse me. Our atomic number for phosphorus was 15, and that's how many electrons it has. Now, again, it would be different if it was an ion. Okay. So we do have some exceptions, some exceptions to the electron configuration rule. And I'm going to pull over here and I'm going to talk about them real quick in the packet, because again, everything is in the packet. Okay, so we have the rules right here, and we have the exceptions. Here's the exceptions right here, and I'm going to go over them. I want you to read through them, but what I want you to do is I want you to notice that if we end in 4D or D4 or D9 or F6 or F13, that's where we have the exceptions. So if I ended in D4, I would add 1 to the Ds and take 1 away from the S's. Notice here, D9, I take 1 away from the S and give it to the D, and this would be the correct one. Same thing would be with if I had F13 or F6 would go to F7, and F13 would go to F14, and we take a 1 away from the previous S. And that's the ones that come through from the previous S. Okay, so that's an exception. Okay, if I looked at our periodic table tells us that. So if we went 1, 2, 3, 4, so if any of these, if we stopped on any of these, we would add 1 to the D's and take 1 away from the S's. Same thing over here. If we were at any one of these, we would add 1 to the D's and take 1 away from the S's. And the reason is because it's more stable. Okay, it's more stable to have your D orbital and your F orbital with 1 in each one or completely full than it is to have that last one be an unshared pair. Okay, so again, notice that we would have this right here, and notice that they put the 3D before this. Okay, you can do it either way. I like just the way the periodic table goes and just write it that way. So your 4S would come before your 3D. Okay, so you look at it either way. I try to change these things when I see them, but they couldn't be. So we're going to basically add 1 to the inner level to make it half full, and then take 1 away from the S. Add 1 to here to make it full, take 1 away from the S. So I'm going to go ahead and do that. This is what they would look like. Okay. So let's look at this question right here. See if you can answer this question. Okay. What is the correct electron configuration of a sulfur atom? Now I'm going to say the easiest way that I think we can do this, because I look at this and I see a bunch of different numbers over here at the end. Well, we can tally up all of them and see what they are and see what that number is. So we have 2, 4, 8, 9, 10, 16. Okay. We have 4, 10, 15. What is it? 10, 16. And we have 10 here, and then we have 18. Well, they all end with 3p. But I can tell you right now, we know that the s orbital only has one orbital, so that can only be a 2. Okay, that's good. And here's our s. So this one, it's not d because this s orbital has 6. Okay, the p orbital has to be filled before it goes on to the next one. So that means in the p orbital, there's 3 orbitals. So that means we have a total of 6. And this one's not correct because this one only has 4. So it's one of these two right here. Okay, now what is the atomic number of sulfur? Well, let's pull up our periodic table. Our atomic number of sulfur is 16. So that means we have 16 electrons that we're worrying about. So our total number has to be 16. But another way we can look at it too is going to be, we know that it's going to be the third energy level. So it's going to end with 3. And this is the P section, remember. So P1, 2, 3, 4. So it should be 3P4. So let's pull this back. And that means that this one is our correct answer as long as it totals up to 16. So I have 2, 4, then 6 is 10, and 2 is 12, and 4 is 16. So C is our correct answer. Hey, good way to figure it out. So there's 3 rules and the key concepts. We're going to go over, we went over them, the off-ball principle, and we need to talk about all those. Here's our definitions that we have. Hey, that's it for me for today and our 5.2 lecture. Hey, hopefully you understood everything that we're going to go on. We're going to practice a lot more on how to do this with the future because we're not going to go on to section 3. Hey, as always, go Mohawks. Nelson out.